So probability So what we're really looking at today is probability involving the word or, okay, or probabilities. Okay, and you're given a couple of formulas. Ooh, I even have a formula sheet up here. So you're given a number of probability formulas, 2 for the word or, and 2 for the word and. So when we talk about the word or, we're talking about a single event. So or involves a single event. Like, I draw a card and I want to know if it's a king or a spade. Okay, so all I've done is one thing, right? I've just drawn one card. I'm not doing two different things. And probabilities involve two different things, right? I roll a die and I flip a coin. So we're doing two different things. Or probability involves you doing one thing. Okay? I draw a card and I want to know if it's. I roll a die and I want to know if it's odd or greater than 5. So that's a single event, or probabilities involve a single event. You're also going to see the words mutually exclusive. And it's talking about the outcome of that single event. Okay, so mutually exclusive, right? It's dealing with the outcome of a single event. And it's tied to the word or. We can only use mutually exclusive if we're talking about a probability that involves the use of the word or. Okay? If it involves and, then all this is us. It's not a single event anymore, and it doesn't involve mutually exclusive or not mutually exclusive. So the opposite of mutually exclusive is not mutually exclusive. Right? No, it's not mutually inclusive or something like that. It's just not mutually exclusive. So dealing with the outcome of a single event. So let's say this event is we draw a card. And we want the probability that it is black or a face card. Do those sound like they are mutually exclusive? No. Why not?
Because there are more cards than just black and face cards.
But there are cards which are both black and face cards, right? So mutually exclusive means it can't be both things, right? So I say the probability, so this is not mutually exclusive. It's not mutually exclusive, right? Black or a face card. Why is it not mutually exclusive? Because there are black face cards, right? Let's say I do something about the probability that my card is a heart or a spade. How would you describe those? Mutually exclusive, right? Because a card cannot both be a heart and a spade, right, at the same time. Remember, we're talking about one single thing. Mutually exclusive, the word or, one single event. That card cannot be both a heart or a spade, right? It's one of, but it's not both. Okay? So this is mutually exclusive, right? This event, because you can't be both a heart and a spade. So how would we look at that? If they're mutually exclusive, which I shall abbreviate mutually exclusive, here's the hearts, here's the spades, right? There's no overlap, right? If you're drawing a Venn diagram, and so all of this is going to go back to set theory and Venn diagrams and all that good stuff, right? So you're going to have to, if there's any weakness there, you got to brush up on that because it's coming in and it's coming at you in multiple units, right? It's in set theory. It's in probability now. So these are mutually exclusive. There is no overlap. Okay? Whereas the other one was black face cards, right? Black face cards. There is some overlap, right? Because we have the jack of clubs, the queen of clubs, the king of clubs, the jack of spades, the queen of spades, and the king of spades, right? Which I have not left any room for in this diagram. We need to make this bigger, so let's just make this bigger. So here, the hearts, right, it's like ace through king, and the spades, it's like ace through king, and then out here, we've got clubs and diamonds, right? And then that would include our universe, right? Our universe is our set of the deck of 52 cards, right? All the hearts are going in this circle, all the spades in this circle, the clubs and diamonds are here. There is no overlap between them. The probability of a heart or a spade, so the or probability looks like this. It's the union, right? It's bringing it together. An or probability is always going to be higher than an and probability, right? Because we're saying, well, any of these will work, and any of these as well, right? So we count them both. Whereas an and probability says, well, it's got to belong to both of them, right? Like, it's got to be this and this. That's going to be a smaller set of outcomes than an or. And so this is the probability of a heart plus the probability of a spade. Okay, and you get this formula, not with heart or spade. It gives an A or B, right? It says the probability of A or B is equal to the probability of A plus the probability of B for mutually exclusive events, right, where there's no overlap. So in this case, we can work this out. What's the probability of getting a heart? So how many hearts are there? It's a good thing they don't really ask card questions on the diploma. 13 hearts. Now, probability is favorable over total. So how many total cards are there? 52. And when we talk cards, we're always talking standard deck, right? If we want to throw jokers in there, then we'll tell you this is a non-standard deck, the jokers are in there. Okay, so 13 out of 52. How many spades are there? Out of? And that's equal to 26 out of 52, which is 1/2. Right? That makes sense. Half the cards are hearts or spades, right? Half the cards are clubs or diamonds. Okay. So, no overlap. These events are mutually exclusive. The formula for mutually exclusive looks like this. The probability of A or B is the probability of A plus the probability of B. You just add them together. Okay, now let's go deal with the black face cards. So there's black and there's face cards. And so in the black face cards we have the jack of clubs, the queen of clubs, the king of clubs, the jack of spades, the queen of spades, the king of spades, right? Are there any other black face cards? No, right? Face cards are just the jack, queen, king. There are 12 face cards in total, right? 3 for each suit. You know, half of them are red, half of them are black. So the black face cards belong in the set of black cards and in the set of face cards, right? Here's our other face cards, right? We've got the jack of hearts, the queen of hearts, the king of hearts, the jack of diamonds, the queen of diamonds, and the king of diamonds. And what are our black cards then? Yeah, so you got the ace of spades, 2 of spades, all the way up to the 10 of spades. Okay? And the jack of spades, queen, and king of spades, right? And we also have the ace of clubs, the 2 of clubs, all the way up to the 10 of clubs. So I have represented all of the black cards inside the black circle, all of the face cards inside the F circle, but there's an overlap, right? Because there are black face cards. So what's outside of the box? Exactly, right? So all the diamonds. So we've got the ace of diamonds to the 10 of diamonds, and we've got the ace of hearts to the 10 of hearts. Okay, I just didn't want to write them all out, but how many cards are in the box? In total. 52, right? How many are in the black circle? Okay, so we're going to do this, right? We're going to do the probability of black or face card. Okay, remember, or is represented by the U, which is a union, which is bringing together, which is making more, right? And I don't care how you remember it, but somehow you have to remember this is or and this is and whatever works for you. Okay, what's the probability of getting a black card? Well, okay, we got ace through 10, which is 10, right? So 10, 20, 21, 22, 23, 24, 25, 26. Okay, so there are, we know that. Why did you count? Over half the deck is black. It's 26 out of 52. Or it's a face card, right? Same formula. Okay, how many face cards are there? Okay, we know that's 12, right? I don't need to count them. There's 12 face cards. What's the problem here? If I just add those together and get 38 out of 52. Problem is, these guys got counted twice, right? Once because they're in the black circle, once because they're in the face card circle, so we need to subtract off black and face card. How many black face cards are there? 6. So this is the probability for not mutually exclusive, right? Mutually exclusive, the circles are separate. What do we call separate circles? Special word. Deals with disjoint, or disjoint. It deals with disjoint, right? They're separate circles, they are disjoint. Okay? If they are disjoint, then they are mutually exclusive. If they are mutually exclusive, then their probabilities are complementary. In other words, their probabilities will add up to 1, right? Because either you're in this, or you're in that, or you're not, right? So if I have the probability of a heart or spade, which is 1/2, then the probability that it's not a heart or spade is also 1/2, right? Those are called complementary events, okay? And mutually exclusive events are complementary, because they have to add up to 1. Okay, so here we go. We got 26 plus 12 is 38, minus 6 is 32. Which reduces to, what? I don't know, 4 goes into them, 8 out of 13. Now, so remember, you can see a probability in a number of different ways, right? You can see it as a fraction. Generally, if we do fractions, then we like to, at the end, reduce it, so we have a reduced fraction. You could see it as a decimal. We could just go 8 divided by 13 in our calculator, right? Get a decimal. You may also see it as a percent. In case we go 8 divided by 13, hit enter, and multiply by 100 to change it into a percent. Okay? So you can see probability in 3 different ways. Right? You may see it on the diploma given as a formula. They might say, hey, is this the formula or is that the formula? Remember, it's multiple choice, right? So you could get an answer to this question. It could be 8 out of 13. It could be 32 out of 52, but that's unlikely. They'll reduce it. It could be the decimal equivalent of this. It could be a percentage rounded to the nearest percent or to 2 decimal places, whatever. Could just be a formula. You're seeing a formula. You're saying which formula matches the situation given. I would say if you're doing these types of problems, draw out the Venn diagram, right? I mean, they call it a graphic organizer. To me, I can't see doing these problems without drawing the Venn diagram out, right? And you start with the overlap, right? Well, how many are in the overlap? Okay, so if we know, well, okay, I've got 6 in here, then I only need 20 out here, right? We could put numbers in here, right? There are 6 in there. There are 26 black cards. So let's just go up here. So there are 6 black face cards, right? There are 26 black cards, which means there's 20 in here, and there are 12 face cards, of which I already have 6, so that puts 6 in here, right? I don't write 12 out here. And 6, right? That would give us a 38. We don't do that, right? We start with the or. We say there needs to be a total of 12 inside the F circle. Yes, there are. 6 here and 6 here. There needs to be a total of 26 inside the black circle. Okay, there are. There's 20 here and 6 here. You don't write 26 in here. You don't write 26 out here. Okay? So that's something you got to work on, right? That's something you need to know before you walk into that diploma, because it's a little weak now based on the on the cume, you're having problems filling in a Venn diagram with the proper numbers, right? You'll get that back once all you all have written, then you get it back to take a look at, right? And there's a few questions I want to deal with on that, because I know they're going to be on that exam, and I'd really rather you got it right than got it wrong on the exam. Okay, so we need to go back and just sort of look at a few things. Okay, so the probability for non-mutually exclusive, the probability is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, and you're going to get that formula. That formula involves 4 quantities, right? 1, 2, 3, 4. Algebraically, if you get 3 of them, you can solve for the 4th. So if they give you this, and they give you this, and they give you this, you just fill them in and you solve for this. Okay, you can work that out. All right, so it's just a straight, all I got to do is write the formula down. You know, here's the thing. You can actually use this formula for all OR probabilities, because if they are mutually exclusive, what's this equal to? It's equal to 0. Right? So it's not going to hurt you if you look at the thing and the formula sheet and you say, I'm not sure which one to use, and you write down the more complicated one, because if they are mutually exclusive, that formula just becomes P of A or B equals P of A plus P of B, right? Because this is 0. All right, I've played all my cards, I've given it away. So those are all the formulas, right? Mutually exclusive. It involves the use of the word or. Okay? The word and has different things that go with it. They are dependent and independent. Okay, so you got to, at some point learn that mutually exclusive and or go together, and goes with the words dependent and independent. And we'll do that, I think, next week. Right. So we got another project workday tomorrow. The next week is just like all math, right? All week. So it's like Monday, Tuesday, Wednesday, Thursday. We're going to finish the remaining sections, review, test. Then Friday's final work on the project. We'll present them the next Monday. Okay, so you got to be here, present your project, or you're going to do it privately with me, or you're going to take a very low mark if I don't see you present. So you need to present it. I need to be present when you present it if you want your mark. Okay, otherwise it doesn't happen. There will be no mark associated with it. So show up. Okay, especially on the day of the presentation. Otherwise, you and your partner, if you're working with somebody, it's 2 of you. I don't want to see one person. You both present it. It means you say, hey, we got to come in and see you. And it's got to be done quick, because marks have to be in by the 10th. Okay? So I don't have much choice, right? If you do not present project to me before the 10th, you don't get a mark for it, and nobody changes that, right? Once marks go up, they're up. That's it. Yeah, they can be changed, but it's got to be some special circumstance, not, oh, I forgot to come see you. Okay. Anyway, let's do some questions about this. So, actually, I wanted to look in the book, too. So here's the book. This is 3.4, Mutually Exclusive Events. And we kind of know what they are now. So it says, Yannick and Violetta are playing a board game. To move on this turn, Yannick must roll either doubles or a sum of 7. Can you get doubles which add up to 7? Are these mutually exclusive or not? No. No what? Just say they are mutually exclusive, or say they are not mutually exclusive.
Oh, no, they are.
They are mutually exclusive, right? Because if I get doubles, what's the sum on the dice? It's either 2, 4, 6, 8, 10, or 12, right? Create an outcome table for the sample space of a pair of dice. So I was looking online and saying, I could just pull one up. But, if you had to create an outcome table for a pair of dice, it's not really that hard. 2, 3, 4, 5, 6, right? Because on the first die, we can get a 1, a 2, a 3, a 4, a 5, or a 6. And on the second die, we can get a 1, a 2, a 3, a 4, a 5, or a 6. Extend this down. And draw this across. Okay, so we'll call this first die, second die, And we're interested in the sum of two dice, right? So you get a 1 and a 1, that's a 2, a 3. Oh, wait, let's do this in a different color. 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9, 10, 11, 12, 11, 10, 9, 8, 7, 6, 5, 6, 7, 8, 9, 10, 9. It fills in pretty quick, right? How many outcomes are there? How many red numbers are there? 36, right? We can do that from fundamental counting principle, right? You got 6 for the first die, 6 for the second. 6 times 6 is 36. There are 36 possible outcomes. Now, we wanted to know about getting a 7 or doubles. Okay, so we're going to go in. Let's circle the 7s. And let's, I don't know, we'll draw a square around the doubles. So 1 doubles, 1 and 1, 2 and 2. Okay, anything on there have both a green circle and a blue square? No. So that makes them mutually exclusive, right? You can either be doubles or a 7, but you cannot be both. Okay. So circle each occurrence of throwing doubles. Shade. I'm not shading. We're not going to shade. We do. What do we do? Whatever. I circled the 7s and I squared the doubles. Sum the two probabilities, right? So I want doubles or 7. Okay, so from this, you could say it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's 12 out of 36, or 1/3 is the probability, right? If we drew a Venn diagram, we would not have any overlap, right? The 7s, we would write down 6 occurrences. I don't know how we do. We either write like a 1 and a 6, a 2 and a 5. You could list the outcomes. Okay, so this 7 came about from a 6 and a 1. This 7 came about from a 5 and a 2. This 7 came about from a 4 and a 3. This one from a 3 and a 4, and so on, right? So you could list those outcomes. I got a 1 and a 6. I got a 2 and a 5, a 3 and a 4, a 4 and a 3, etc. Okay, then I could list the outcomes for doubles, right? And then I could list all the other outcomes, and they would look like this, right? There'd be 7s. And there'd be doubles, there'd be no overlap between them. No overlap means that they are mutually exclusive. Mutually exclusive is tied to the word or. Or probabilities are a sum of the individual probabilities, and if they're mutually exclusive, there's no overlap. We don't worry about that. We won't count anything twice, right? 7s are counted, but they're totally separate from doubles. Okay, and so... Oh, here's one here. Carlos drew a single card from a standard deck of 52 playing cards. What's the probability the card he drew is either an 8 or black? Are those mutually exclusive? The question you ask yourself for mutually exclusive is, are there black 8s? Yes, there are. How many? 2 of them, right? So that would be in the overlap if we're going to do black and 8. Right? There's black, there's 8, and there are black 8s, right? We draw those as overlapping. Notice, single event, drew a single card. Single event ties in with the word or, which ties to the concept of mutually exclusive or not mutually exclusive, which gives you one of these two formulas involving the word or. Okay, wait, let's erase. On the screen. Okay, so that's how they introduce it, and then here's how they develop the formula, which is actually kind of interesting in a sense, because it goes back to numbers, right? So if you remember, probability is the number of favorable over the total number of outcomes. The number, so it's the number of A union B over the number in the universe, right, which is in the box, which is the number of A plus the number of B. Remember, or is associated with the operation plus. So it's the number of A plus the number of B. You could split this out as a fraction and write it as n of A over n of U plus n of B, right? This has a common denominator. You split it out like this. Number of A over the number in the universe is actually the probability of A. So that's sort of a derivation of the formula, right? Where does this formula P of A union B equals this come from? here's where it comes from, using the numbers, right? Now, they're very similar, right? Where you see a P, you could really replace it with an N, right? The number in A union B is the number of A plus the number of B. So you kind of have those formulas here as well, right? The ones for numbers when you're doing questions just involving set theory. So it's very important to read the question. Are they asking for a probability here? Do they just want to know how many, right? What's the number of things? Or do they want a probability of something? Okay, let's go to another example of given probably you get well, let's do a black or 8. Black or 8. Okay, so seeing that, you then need to think, okay, probability of black or 8 is the probability of black. Let's clean that up. Plus the probability of 8. And now you ask the question, is there an overlap? Are there blacks and 8s? And you say, yeah, there are. So then we subtract black and 8. Okay. Do we need to do a Venn diagram? I don't know. How many black cards are there? 26 out of. Okay. So remember, these aren't numbers, right? If we were counting the number of blacks or the number of 8s, but these are probabilities, so it's favorable over total. How many 8s are there? 4 out of. How many black 8s are there? 2. Okay, so that's 30 minus 2, which is 28 out of 52. And let's divide by 4, so that's 7 out of 13. Or whatever the decimal equivalent of that is, or multiply the decimal equivalent by 100 to get a percent. And you'll get. Okay? And if you need to, draw a Venn diagram for it, right, to help you count it out. And if you do the Venn diagram, so black, 8, you don't necessarily have to write down every card, right, as in ace of spades. You could just do it with numbers. You say, well, I know there's 2 black 8s, right? And I know that there's 4 8s altogether, but I've already got 2 of them, so I only need another 2 there. I know there's 26 black cards, but I already got 2 of them, so there's 24 there. Okay, now if I want to do OR, I just go 24 plus 2 plus 2. 24, 26, 28 out of, well, there's 52 in the box, right? So you get 28 out of 52. So you don't need to use the formula, right? You can use a Venn diagram. How many of these are there that belong to both sets? Leaving how many in this set? Leaving how many in this set? Count them each once, right? Union, just go 24 plus 2 plus 2 is 28 out of total, their cards, 52 cards, is 28 out of 52, right? Or you can do this, okay? On the diploma, who cares? Who knows? Nobody knows, nobody cares, right? Nobody's going to look to see, did you write this down? Did you write this down? Did you write anything down, right? You don't have to write anything. However, I advise writing stuff down, okay? Do the diploma in the book, right? Show all your work for everything just for you. Nobody's ever going to look at it. But show the work just for you so that you're making sure you're writing down the correct formula or you're showing this. For sure, circle your answers and write your numeric response in the book. Okay? Why? Why would you do that? Because if your Scantron sheet gets lost, then they can go and look at the book and they can mark the book. They get both, right? They'll get the book, they'll get the sheet, both of them will have your name on it, okay? If something happens, and it's like, well, where's the sheet for so-and-so? Oh, don't know. What happened? Oh, that wind came up and, blew open some books and these things went down a sewer grate or whatever, right? If that happens, if your book is marked and everything's in there, they can take your book and just sit down by hand and just go, If your book is blank, what's going to happen? congratulations, you have won a free rewrite of the diploma exam at a center of your choice. You can do it in August, you can do it in November, whatever, right? Okay, something happens. Let's say, I don't know, you're Scantron, you get your marks back and you think, there's no way that I scored that. It's not possible. I could not have got that mark. And what may have happened is you put the answer to number 1 in number 2 and you kept going and then you didn't notice when you reached the end and everything's off by 1. Well, they're going to mark the sheet and you're going to get this mark back. What? No, I did not get 25% on this exam. I know I did better than that. You can appeal it. And you could say, well, can you look at my booklet or something? Like there's something wrong. Maybe the sheet scanned incorrectly. Okay? If it's not marked in the booklet, there is nothing they can do, right? There's nothing to look at. So do everything in the booklet. Show all your work. Right, let's go back to the book for a sec. All right, so here was a little derivation of the formula. Let's move down. There's some board game. We got sums of dice. Okay, what's this one? Recall the board game. According to a different rule, if a player rolls a sum that is greater than 8 or a multiple of 5, the player gets a bonus of 100 points. So greater than 8 or a multiple of 5. So the multiples of 5 are done in yellow. The greater than 8s are done in red. But there are some which are both yellow boxed and red, right? Now, if I want to count these from this, I can just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and say there are 14 outcomes. Okay? I'm not using any formula. I'm just looking here. There are 14 outcomes that are favorable. And it's 14 out of 36. Okay? If we do it by, okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these, and there's 1, 2, 3, 4, 5, 6, 7, and there's 7 of these, which is 17, and then we have to subtract the overlap of 3, right? Or you just count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Just count everything once. Don't count something twice. And you can do that. Okay? So here they're going to show you using the formula. There's 10 and there's 7, and that's going to give us the end of the page. It's going to give us 17 out of 36, and but there's this overlap here, and they get into the big formula stuff. All right, what happened? They get into big formulas here. Don't worry about this stuff. You're not going to have to worry about that. Worry about this stuff, right? There's 10, and there's 3, and there's 7. Okay, so that means that there are, well, that's 10 total in here, right? That's not how we would do the Venn diagram. We'd say there's 3 here and 7 here, and there's 3 here and there's 4 there. It'd be 7 and 3 and 4 is 14. So that's not really a great diagram for the way that we've done things. Okay, but it comes out to 14 out of 36, which reduces to 7 out of 18, or 38%. What does it do? Just leap to the top of the page? Or? Using a Venn diagram. Oh, come on. Okay, again, Venn diagrams are good, right? That's how I would do most of these questions. And you can look through them, look at how they use, put this in here, put that down there. Don't worry about formulas like this. See these formulas, probability of B subtracting L. Let's actually move. I can't do the bottom. Going all over the place. Yeah, this probability of B subtracting L, I do not think you're going to see this. However, I'm going to advise that you at least read through and look at this and just try and figure out what they're getting at. Because I want to cover my bases so that if on the test they actually show. Like, I think there is next to no chance, right? I'll give you like a probability of 1% that you will see something like that. Okay? So take a look at it just for your own use in case you happen to see it on the test. I'm not going to test you on this. I won't do it like this, right? We do this, but we do it without these formulas, right? We just do it by saying, well, there's 8 that are here, and there's supposed to be 62, so I fill in this number is 54 or whatever, right? So we do this, but we do it without using the formulas and stuff. We do it by filling in a Venn diagram. And that's all I would expect you to do on this type of question on any test I give you or the diploma, right? It's just fill in a Venn diagram, throw in the numbers, and then figure out what numbers go in there. That we know how to do, not using these formulas. So I think there's next to no chance that you're going to see one of that using this formula on the diploma. Okay, so don't waste a lot of time on that. Yeah, you can look through these ones as well. Just going all over the place. Determine the probability of 2 events. Let's take a look at this one. Car manufacturer keeps a database of all the cars that are available for sale at all dealerships in Western Canada. For Model A, the database reports that 43% have heated leather seats, 36% have a sunroof, and 49% have neither. Determine the probability of a Model A car at a dealership having both heated leather seats and a sunroof. So let A represent the set of all Model A cars, and L is the cars with leather seats, and S is the cars with a sunroof. Why are you... Why can I... Okay, you know what? Let's just go to 100%. Fit visible. Actual size. Nope. Zoom to page level. All right. There we go. You can still see it. It's actually in your book anyways, right? 172. And it's the wrong page. 173. 174. Is this it? I think so. Here we go. Yes. So 49% have neither, then 51% have leather and. Okay. Now, probability of leather and is probability of leather plus probability of sunroofs minus the or. If 49% have neither, then 51% have leather or sunroof. There's 51 in here. Okay, and we know that, what do we know? 51% is 43. So we've got 43 and 36. So the way we would do is say 43 plus 36 is, 79. Okay, so we have to have 79, but there's 51. Okay, so we would go, all right, 79, but I've got 51, which means there's 28 that have both, right? So there's 28 that go in both. Then this has to be heated leather seats, which is 43. So 43 minus 28 is 15, so we get 43 in here. And the sunroof one is 36. We already have 28, so there's 8% in here, giving us the 51 in here because there's 49 out there, right? 49 out here, 51 in there. But these give us a total of 79, so we put a 28 in here, right? Without the formulas we do this. We just kind of add this up. So the probability that has both is 28%. Okay. What's next? This is just the summary. I wouldn't worry about these formulas too much. Not this formula, for sure, right? And then just remember mutually exclusive, etc., etc. One last thing with probability. One last thing with probability. Actually, two last things. No, one last thing with probability. Expected value. Or how many things, right? So if we have n items, with a probability of p. So let's say that there are, 400 students graduating, and the probability that any one of them will forget their grad gown on the day of is 0.01%, right? We're going to say that not many people are going to forget, so or 0.1%. So there are 400 students. And not from this school, obviously, because none of you would forget here. So there are 400 students graduating. The probability of forgetting the grad gown 1%, how many will forget? Okay, so to get the number of people that will forget it, we take the number of items, in this case 400, times 0.1%. Now that's got to be changed to a decimal, right? So what's 0.1% as a decimal? That's right, that is 0. What is it? Work it out. You got to calculate. How do you convert a percent to a decimal? Divide by 100, right? Percent means out of 100. So divide by 100, and what do we get? 0.001? Okay, what's 0.001 times 400? 0.4. So 4/10 of the student will forget their dragon. Or what that likely means is over the years, right, and in order to get this up to 1, probably in about 3 years, somebody will have forgotten it. In 3 years, right? So if you want to work out the number of, I know how many things there are, and I know the probability of an event happening, I multiply the number by the probability, but it has to be expressed as a decimal, right? So expressed not as a percent, expressed as a decimal. And then I can figure out how many of these things do I expect, right? How many of these things do I expect? All right.